So today we have some ferromagnetic materials, and if you take a nail and you stick it to a magnet, then we can make this nail stick. So I have some nails here, and I have my magnet. So, okay, hold on a second here. Okay, these nails are apparently not sticking to our magnet. So let's see if we can use some physics to make these nails stick to the magnet. So let's go over to our notes. So the magnetization of a material actually depends on the temperature. So atoms in a material are randomly oriented, and so the material doesn't appear to have any magnetization, and this is coming from thermal motion. If we stick this material in a magnetic field, the atoms tend to align with the magnetic field, but they're still going to be moving because of temperature. So what we can do is decrease the temperature, and that decreases this thermal movement, and now our atoms are easier to align with a magnetic field, and we can get some more magnetization. So one relationship was discovered 100 years ago or so. This formula, which gives you the magnetization based on some applied magnetic field. So just to go through the terms here, M is this magnetization of the material. B, applied, is the magnetic field in Tesla. We have temperature dependence here in Kelvin. There's the Boltzmann constant in here, which you often see with next to the temperature. The MS is what we call the saturation magnetization. This is the maximum magnetization that the material can get. And then this little m is the magnetic moment of an atom. And typically we use something like MB, which is the Bohr magneton. And that has this value here. So what does this formula look like as a function of the magnetic field that's applied? We see that this is a straight line. And so M depends on the magnetic field linearly, as we can see here. And there's this saturation magnetization here where these lines cross. And in actual practice, what happens is this formula isn't quite right. The actual magnetization sort of approaches this saturation value. But this is a pretty good relationship. It's linear over over much of the magnetic field that's applied. So what's the bottom line? The bottom line is that magnetization increases as the temperature decreases, like 1 over T, and the magnetization increases as the applied magnetic field increases. So what we want to do is we're going to decrease the temperature of our nails. And I can tell you that these nails are made of a material called monel, which is an alloy. And this alloy basically becomes ferromagnetic at around minus 100 degrees Celsius. So how are we going to get to minus 100 degrees Celsius? Let's go back over to the experiment. So here we are. We have our magnet. I have these monel nails here, which do not stick. But what I do have is some liquid nitrogen, which has a temperature of minus 200 degrees Celsius. So this should be good enough. So let's put our nails in here and kind of fill these nails up with liquid nitrogen. Okay, we can hear them bubbling. And we're cooling these things down. When it stops bubbling, I'll know that these are at a temperature of minus 200 degrees Celsius. And now let's see if these nails are magnetic. Okay, and indeed, we see that we have, at this temperature, below minus 100 degrees Celsius, these monel nails become ferromagnetic, and the magnetic moments of the atoms are all aligned up with a magnetic field, and we have a nice magnetized material. So there you go. It's not magic, it's physics, and I'll see you next time. Well, thanks for watching. It looks like I survived today. But if you want to find out if I survive the next experiment, then remember to click like, click subscribe, and I'll see you next time.